Discussion in this PowerPoint is only about 3 slides long. I was going to dispense with it quickly before I start with a larger subject. I thought Fridays are a great day to introduce large subjects because who's going to skip a 2 p.m. class? None of you, obviously. So I was talking about keys, and I remember that when I introduced this slide last time, I basically parroted the first line on this slide. We need a way to uniquely specify how tuples in a relation, how rows in a table are distinguished. And nobody questioned me. Why? Why do we need a way to uniquely specify how rows are in a table are told apart? Why is that essential for the efficient running of a database? It has something to do with sorting, and in CS2 we learned some sorting algorithms, and we learned that for the most part you can't sort faster than in n log n time. I mean, people will say, well, no, wasn't there that one button? No, we can't use that everywhere we want to use that. We can't radix sort everything in the world. Radix sort assumes that everything in the world is the same length, and nothing in a database is the same length, and so we would have to do additional processing. We're going to ignore radix sort, and so that means if we want to get anything out of a database, if we want to get a list of values out of a database in some sort of sorted order, it's going to take us n log n time. Databases have a whole lot of data in them, big long lists of values, and of course n log n time gets larger and larger as the size of the values that you want to retrieve increases, but at least it doesn't increase on an n squared type rate. We can't get it down to increase in time linearly, but if we have to grab data out of a database and we need it sorted in some way, I want to print all of my professors' names in alphabetical order on the web page, for example, and they're not already in alphabetical order, then I'm just going to grab them out in whatever random order they're in, and I'm just going to sort them using quicksort, and that's going to take me n log n time, and then I'm going to be able to put that up on the web page. And I don't know, I told you that there is a logical view and a machine level view of these things. We don't really control the way data is ordered on the disk, but it's going to be ordered somehow. It's probably going to be ordered maybe in the order it was input into the table. Maybe that would make sense. Or maybe if we're really concerned about accuracy, we would like to place data in the machine in the order that we would like to retrieve it most of the time. Maybe that would suggest that we should store our data in alphabetical order for students and instructors, because why would we retrieve those data values in any other order? Well, I'll tell you why, and it has to do with that schema diagram that none of you have out yet. I don't even know where my schema diagram is. Oh, there it was. I saw it just for an instant. Okay. You recall that when I was talking about the data in the student table or the instructor table, and there was this one specific attribute that could be used to represent that entity in any other table. So if any other table needed an instructor ID, we wouldn't copy something expensive like a name string or something. We would just put a short little ID data type in there, and that would represent everything else in that table. Right? And so, if every other table in your system is using instructor IDs to represent all the other data on the same row for the instructor with that ID, then maybe we should rather store our instructor data on the hard drive, it sorted in order by instructor ID, by star ID order. ascending order, right? But now Sam's going to raise his hand and tell me, but we never want to see instructor data in star ID order. That doesn't make sense. What's pretty to our human eyes is seeing the stuff in some sort of sorted name order, right? Star ID order makes no sense to us. Our star IDs have no relationship to our names or anything, and we're just going to see the names of our instructors, if they're sorted in star ID order, in some just crazy random order. What if I need to find Neville in a list of 100 instructors? Normally I would look in the middle of that list, but now if it's in star ID order, Neville could be at the top of the list or the bottom of the, I have to look sequentially through the entire list. So there's a conflict there, right? The database would like everything sorted in the order of the primary key values, the representative values in those tables, but often when we want to display data, those numbers make no sense to us. That helps the database work, but we want to show things in another order. And so that's what leads into why we would want a primary key, and primary keys are built out of values that are unique, because that way we know they can be ordered. And if they can be ordered, then we can find them quickly with an algorithm like binary search, for example. And so that makes things work efficiently in the database. But also, we want to know that we can also retrieve things in another order efficiently. And it would be great if we could if we could get them in that order in less than n log n time, because that would beat the standard time that we would have to wait of grabbing our data in whatever random order that we don't like is and reordering it in a way that we do like. But that would take n log n time. And so now I'm not only talking about primary keys, but I'm talking about indexes, which a primary key is really an index. It's just the index that we expect to use the most, and the indexes that we're choosing in here are the indexes that are most convenient for the database, which is nice because now we're guaranteeing that the database can get data as quickly as it possibly can, so that the whole program will feel good to us. But we still would like to be able to grab student data out in name order, say, efficiently, because every time we print a report with student names, we're ordering those students by last name, right? Again, sorting students by star ID isn't super helpful to us. And so for those of you who have always wondered in CS2 and C++, why do I have to learn what a pointer is? An index is an array or a vector of pointers. Again, a pointer is just a memory address, it's just an integer, it's a cheap data type. It takes as little space as possible compared to all the other data types. And so the index for our primary key, say, let me just imagine that I've got, I don't know, a student ID and name here. I don't have the other stuff, but the other stuff it goes behind the screen. I just drew the first two. And let's say that it's arranged in a particular way in the data, physically on the database. And in fact, it's arranged in such a way, I just printed the first letter of the last names, and so we can see that students are ordered but in last name order for whatever reason. Maybe it's just luck, maybe it's randomness that actually placed them in that order. I don't know. But anyway, we do know that for the database will want to be able to retrieve those names in star ID order, because that would be more efficient for it. And we know that the database could just grab all those names and sort them in n log n time, log linear time. But this index is actually going to help us do it better, because since this index is just a list of pointers, all we have to do is run the sorting method once, and we're going to sort the pointers, what they point at. We're going to sort them by their values, we've chosen the star ID to be the value that they sort on. So they're not going to sort on the letters here. They're going to sort on whatever numbers are here. And I didn't write numbers because I didn't want to have to be accurate and draw my arrows to the right places. But you know how I represent pointers on the whiteboard, right? It's just arrows. I'm just showing you which address that pointer is directing me towards. And so maybe if I look at all the star IDs, the smallest, the alphabetically least star ID is this one down here. And the next one is, oh, actually, it was the second one in that list too. And you know, basically, up and down here and up here. And this looks messy and all, and I mean, that's what things are going to look like when you're looking at data types. And oh, this guy is actually all the way up here. So, worse than a butterfly ballot. But what happens when I have an index of pointers, a vector of pointers, ordering a bunch of stuff in some other order? If I want to retrieve them in this case, star ID order, I just first retrieve the guy that this guy is pointing to, then the next guy, etc., etc. How long is it going to take me to retrieve them in that order? Linear time. So if we can do the log linear work once, and as long as the data doesn't change, then we're going to be able to use that list of pointers to retrieve our values in minimal sorting time. It requires a little bit of work up front, but this is how databases save time down the road. Yeah?
Yeah, not only that, but most of the time the ID is unique to that one specific instance rather than, you know, there could be multiple of the same thing.
Sure, multiple Joneses.
Yeah.
Multiple John Joneses.
But in order to get the right one, usually
that's why
grab the ID.
That's why we give you a star ID, and we're guaranteeing you that your star ID will be different from everyone else's. So even if there's another Michael Wright, even if the entire Wright family with all of your Michael Wright cousins are on campus or have records at this university, you can give your star ID, and that'll take you directly to your own records. Yeah.
Mm-hmm.
So that's why we need, when we're building these tables, we need to identify a field or a combination of fields that will uniquely identify these things, because as you saw from the page I was on, I don't even remember what it was anymore. Let's try page number 19. Oh, that's too far. 17. I don't think so. Okay, this one. 21. That's why we need to be able to uniquely specify how rows in the table are distinguished, so that eventually we can retrieve those rows in any order that we want, as long as we have previously defined an index for that ordering scheme. And this means that when databases retrieve values from their tables that have been previously ordered, they will fantastically retrieve them in linear time, which up to today I didn't even think was possible. So otherwise, this slide sort of steps us through some stuff where I kind of wonder why I need to know what a super key is, but it's a super key is something that is possibly a superset of something unique, but you know, it's a possible combination of things that can be used to order the values within that table. And then we just want the super key that has the minimal number of values, so we have to spend the fewest operations evaluating them, and so all of those are a candidate key. And we could have multiple, I don't know, like even in the instructor or student table, multiple single columns that are unique, right? I mean, it's not in your schema diagrams, but if the student table included a social security number, right? You guys probably all have a social security number. That would also be useful for ordering unique values for ordering the students in social security number order. The reason, probably, that we don't, well, there are several reasons why we don't use your social security number in a university database. First, we don't want to get sued if ever the university database is hacked, and that's why we make up a completely other, different, unique value for you that we can use without fear of being sued. But also, if we did use your social security number, if star IDs didn't exist, that means that your social security number would be in multiple tables throughout the database. Your social security number would be copied in multiple places. That just sounds like a terrible idea, even if we believe that our security is such that we are unhackable, because our security is never such that we are unhackable. And I mean, we do have some of your social security numbers. I don't know if when you registered as a student, you had to give your social security number. Maybe we have all of your social security numbers. But I know that those of you who are working at desks doing work study throughout campus, at least those people we do have social security numbers for, because if you're getting a paycheck from the university, the government wants to make sure you're reporting your income and all. So. There are your social security numbers, at least for some of you, in the database, but even though we know that's a unique identifier, we're not going to choose that candidate key to be the primary key, just because we feel that spreading private information like that around is probably not a good idea. Great candidate key, we're still going to choose star ID as our primary key, our primary means of ordering things, and our primary means of referencing rows in particular tables, in any other table that might potentially need to be connected to that table. Yeah.
If you're wanting to just access the students from BSU, you could use the tech ID as well, the little student tech ID that they give us as well.
Yeah, probably. Yeah, I don't actually. Yeah, I don't actually know which ID the university uses for students here, but they probably use a system-wide one because they want to eventually be able to merge our data with Mankato's data in case they need to generate certain reports. So they're probably using something that is going to be in common with all the other universities in the system, just for ease of gathering data together.
Yeah.
Because again, the whole thing that makes these databases possible is multiple tables using the same values, and so multiple databases using the same values that mean the same thing in all of those databases. That is like gold. That makes databases instantly connectable. If we have a field like that we can count on being common between all of those different storage locations. All right, so finally, I think I got to this slide too. A primary key is just one of those candidate keys that's guaranteed to be unique, and we just choose it as a data value that's safe to spread around and to store in multiple tables. We know that it's minimal in size. It's generally an integer type thing. When you're creating a table in Microsoft Access, that's why that field is called auto number, that it always tries to put out there. It's generating an integer ID in order for you to be able to represent your rows using that number in other tables, should the occasion arise. And so that key, has some meaning for the table as a whole. And of course, those values are unique, so that no two tuples will have the same value, just like no two students have the same star ID or tech ID for that matter. Why does your choice of primary key represent a constraint in the system? What's a constraint? It's a limitation, right? What limitation are we imposing on ourselves by choosing star ID rather than tech ID rather than social security number?
We're basically doing an internal one that is unique to each individual tuple.
Yeah, we're making a choice as to what kind of data is going to represent our rows, and I guess the real world constraint that imposes is that value is going to be copied in other tables to represent those rows. And if ever a row disappears out of that source table and that numeric ID goes with it, then all of these other tables suddenly have this useless number that doesn't connect to anything anymore. And so the constraint is you're making that number very important. That source table better not lose data. You better not have any student workers who don't know what they're doing, who destroy data without knowing it or without meaning to, right? And we're always going to have student workers like that. And so that's why the number one job of a database administrator is maintaining your backups. So if data does go missing, we just rewind to an hour ago when the data was last backed up, or at least last night, midnight is generally when institutions back up their data. So you may lose one day's work, but you're not going to lose records that were put in here 20 years ago and never used since, but they still have references in other tables that would make those rows go useless. Data takes up so much room in our database, we don't want any useless rows. And over time, you can even tell on the internet, which is basically a great big interconnected sort of database system, maybe. That's not very easily searchable. Because we don't have indexes. Oh, we need indexes. I guess that's what our bookmarks are in our browsers. But our bookmarks tend to be rather, just self-selected, a little a subset of the internet. It's not the whole thing, so I guess I can't call it an index of the internet. Well, what rabbit hole have I just gone down there? What was I talking about?
Primary keys.
I was talking about primary keys and how they're constraints. Oh God. I need somebody to rewind that video that they're making in the back of the class there. All right. Well, maybe somebody will send an email. How important could it have been? Well, let's talk about some set theory, and I'm basically just going to repeat a lot of the stuff that was on the previous two slides, but I'm just going to do it in, sort of a variable set theory form. So let's look at the definition first, off to the right. Capital R it represents the set of all of the attributes, that's the column names, for any given table, lowercase r, right? So whatever value is in lowercase r, that's the name of a table on your schema diagram, and uppercase R is that list of attributes inside that box with that name, right? And so we're going to say that K, capital K, is a subset, or possibly the includes the totality of big R, which is what again, Sam? What is capital R?
Attributes. Oh,
Attributes of what?
the relation of small r.
What are the attributes of small r?
Great question.
All the column names,
All the column
right? So what does it mean when I say that a capital K is a subset of R? A selection of those column names. It could be one, it could be all of them, or it could be somewhere in between, right?
Okay.
R is the complete set of all column names in your table. K is a subset of those column names, and the definition of subset is inclusive of it could be all of them. So why are we defining some set K, which could be one, or could be multiple, or could be all of the attributes of some given table, lowercase r? Because we're trying to define superkey in terms that would make a mathematician smile with pleasure. And so K is a superkey of R if the attributes within K are sufficient to identify a unique row in each possible table named lowercase r containing the attributes uppercase R, right? We're just saying the same thing that I said two PowerPoint slides back. A superkey is any collection of column names that uniquely identify every single row in a table. So for the student table, for example, ID, a single attribute, is enough to uniquely identify a row. But if I were looking at somebody's schema diagram and looking at, say, the teachers table, if you guys are looking at your local teachers table, you're going to realize that in order to identify a single specific row in the teachers table, that requires all 5 of the attributes in that teachers table. They're all underlined. And underlining means all of the underlined things combined together in order to be able to specifically identify a particular row. If you're looking at the time slot table, then you only need 3 of the 4 values. Only 3 of the 4 of them are underlined. So that's what the definition of superkey is in set theory speak, is one or more attributes which combined make for a unique ID that uniquely identifies any given row in that table. And we're using the generic variable lowercase r for the table name. We're using capital R for the set of all column names, all attributes of that table. So if we're looking at the instructor table, you probably remember that line from 2 slides ago. If we're talking about the instructor table, both ID and ID name, both of those sets of attributes are sufficient to uniquely identify any given row in the table instructor. So you remember the candidate key definition, right? We're just going to say it again in math speak. Since we can have multiple superkeys, those superkeys that are minimal, we can also give them the name candidate key. That is a superkey, a collection of attributes that is as small as possible. Those are candidates for being primary keys. That's where the candidate name comes from. And so out of those 2, the reason that ID, comma name, uniquely identifies everything is because ID is already uniquely identifying everything. And so why use more attributes than you need to, more columns than you need to, if one column is already doing all the work for you? And so that's why we say out of those 2, the ID is the candidate key, because ID name is just using more information than it needs to do the same job. So yeah, I added that when it occurred to me one day that SSN, Social Security number, would also be a candidate key of the instructor table if the instructor table had that attribute. Yours doesn't, but there's no reason why a table should only have one candidate key, just like there's no reason why it should only have one super key. So that's why we say one of the candidate keys will be selected to be the primary key. We're going to go with whatever seems safest to us. SSN, I don't want to spread that around, so I'm going to choose ID, the star ID field, as the primary key. That's the one that I'm going to click the little golden key icon in Microsoft Access and make a vector of pointers to whatever order the data is already sorted in, or it's probably just in random order on the hard drive. I'm going to make sure that those pointers have done the sorting for me, so I can just go down the list and retrieve those values in that order, and that's going to take me linear time. All right, we have a new concept here. I haven't talked about foreign keys. But really, the foreign key concept is, you know how that primary key in one table is used as the representative in other tables? And so for the ID field in the instructor table, you see ID in another table that's referring to instructors. And that's basically saying, okay, when you find 17 back in the home table, that's the all of the data that this represents is going to be right there. So the foreign key is the value in one table that must have a matching value in the home table. So a foreign key is the instructor ID in any table that is not the instructor table. The instructor ID is the foreign key value in every other table that needs to refer to those instructor values. And they only have the instructor ID to represent those values in that table, right? We don't want to have to copy instructor names in multiple tables. We're just going to copy the instructor ID in the table. That instructor ID does not come from that table. That instructor ID is a foreigner in that table, and that's why we call them the foreign key value. All right? And in order for that foreign key value to make sense, then for that 17 to make sense in, I don't know, the teaches table, then we need to have a row with ID 17 in the instructor table. So that's what it's saying when it's saying it must appear in the source table, is if that row does get deleted out of the instructor table, there's no more instructor 17, we fired that guy. Any other records that refer to instructor 17 have nothing left to connect with. Those records are now wasted space, essentially. So, again, this is probably beating a dead horse, this is obvious, but the referencing relation in the referencing table in the foreign key connection, those lines with arrows, arrowheads on your schema diagrams, they're showing you the arrowhead, I think, is pointing to the source table, right, where that data value is coming from. And so the end of the line that doesn't have an arrowhead on it is where that value is copied, but where that value is considered to be the foreign key value, right? And then that's one reason why I got so upset when I did find a single line on that entire diagram that didn't have an arrowhead anywhere, because it really did need an arrowhead. And now you guys can tell where that arrowhead belongs, right? Where is that value coming from that is being copied? Which is the referenced relation, that's where it's coming from, and which is the referencing table, that's the table that contains that value, even though that value represents an instance in a whole nother table. Make sense? Then again, I don't know if we're ever going to see referencing or referenced again, but we're basically talking about one end of that arrow connector or the other when we're talking about that. But really, it's this foreign key concept is what underlies how we're able to tie tables together in the first place. Your very first homework 1, you created two foreign keys from two tables that you put in the glue table, right? The glue table referred to two other tables. The glue table was the referencing table, and the reference tables were the other two tables that you were putting together so that you could concatenate the perfect rows together to represent whatever that database system was trying to represent. All right, I think that's the last bit of foreign keys there. Oh, here's another copy of my schema diagram. I could have used that 5 or 6 times in the last 5 minutes. But okay. Oh yeah, so here is that line with no arrowhead. Between those two tables, section and time slot, which is the referencing table and which is the referenced table?
Time slot?
Time slot is which?
The reference table.
That is correct. We are taking the value time slot ID from the time slot table, and we are storing it in another table in which it is the foreign key. That is the referencing table, this is the referenced table. We don't, once that value is in that section table, we never want to lose that value from the time slot table. And so that introduces the next concept, referential integrity, yet another constraint on our databases. And that refers to the requirement that the values appearing in, that the values, I don't know that I like that language, that's not what I was about to say. That the values appear in the specified referencing relation. I mean, I guess that makes sense. But what I think that means is the values that we see in this table, the foreign key values, appear in the referenced table. But I guess, because I don't think there are any problems if I've got a time slot ID number 17 in this table and nobody else uses time slot 17. I don't think that causes any problems. I think that the problems are caused when the course section says, oh yeah, I'm being taught in time slot A, and there's no time slot ID A in the time slot table. Now, I don't know what time that class begins or ends. So, I think that came directly out of the book, but maybe that was mistyped, or maybe I'm just misunderstanding it. But anyway, it has to do with using foreign key values to tie rows together in multiple different tables. The purpose of referential integrity constraints is to ensure that there are valid associations, that is, the numbers that we see in the referencing tables have explanations, have associated values in the tables that are being referenced. Because yeah, we're not storing start time or end time or day in the section table. And so the section table is reliant on having a matching value in the table that it references in order to say that this course that is being taught in this section in this semester, in this year, is taught on these days from this time to this time. And so now we're talking about deleting records from tables. And so if we delete a record with time slot ID from this table, that doesn't change anything. Our database can go on. The integrity of our data referencing system is maintained. But how can we break the referential integrity? Is if we have references to time slot ID A in this section table in multiple rows, and we delete time slot ID A because we decide that we are no longer going to hold classes from 9 to 9:50 a.m. on Monday, Wednesday, Friday. I think that's the one I'm always talking about being identified by the letter A. And so maybe administration has decided, okay, we're never going to teach classes from 9 to 9:50 because we want to have a time during the day where nobody has classes so we can call for campus-wide meetings, which the students are sure to come to, right? Because you're not going to have any conflicting classes. There are no excuses. You're all going to troop into that big presentation room in this building on the first floor from 9 to 9 a.m. to hear what the president has to say. Important announcements, weekly. Keeping you up to date on what's going on campus. You'll all be there, right? I mean, we've actually talked about that. There are universities that keep like 11 a.m. to noon or something free exactly for those reasons on like a specific day of the week, like Wednesdays. They're not going to do it on Fridays. You know why? Because people drive home on Thursdays. It has to be Wednesdays. They don't even come back until Tuesdays sometime. We can't do it on Mondays. Anyway, that's an idea that has been brought up multiple times in teacher meetings, and it never goes anywhere. All right, hey, I think I'm done with, that boring set theory stuff. We made it through. We probably don't need to know about set theory. When are we ever going to need to know any of that stuff ever again? Hey! Do you guys remember how much you loved your algebra classes? You loved algebra, right? most especially you loved it in memory when you were sitting in calculus class. Because boy, wasn't math easy back in the algebra days? You're sitting there figuring out freaking derivatives, and what's that big S symbol, the opposite of derivatives? Tyler, come on. You're the math dude. What's the opposite of taking the derivative of something? Building a better integrating. So I know we talked about it a little bit in algebra, but we didn't need to know how to actually do that stuff to pass the exams. So, we didn't study it that much. But then in calculus, it was all integrals and derivatives. And I'm thinking, oh man, why can't we just be foiling stuff? Foiling was, compared to this, it was pretty easy. So with that in mind, let me show you 3 possible languages that we could use to explain the next concept. I want to explain how query languages are put together, and I could just give you the code words. That's how you learn a new programming language. But we feel like students can benefit from a little theory here. And so first I'm going to try to give you some of the mathematical underpinnings of query languages, because we don't want to have to worry about the details. We just want to know what's going on. What is the actual operation happening here? And so as we develop our query language, we can develop it with, in terms of a programming language. Programming languages that we learn tend to be procedural. That is, this thing happens before this thing. We just make a list of the order in which things should happen, and that's how we define how tasks are done. And that's how we do a lot of math in math classes until we come to differential equations classes, where sometimes the teacher says, well, we could do this or this or this, and we don't know which approach is going to be best, and so we're just going to guess. We're going to just choose one of these things at random. And if it doesn't work out, then we're going to back out of that and then choose another approach. God, I hated differential equations class. I was yearning for some proceduralism. I want to know exactly what to do in every situation, and they were telling me to make a random choice. So we have procedural languages, we have non-procedural languages. Most databases, if you have to program up a new database to compete with Microsoft Access, are going to use elements of both. There's no escaping it. But if we are talking about, representative mathematical languages that can represent something like a language, like SQL or Python, we can represent them either in a form called relational algebra. That's a procedural language. That's something that I'm used to. Or we can represent them in a form called tuple relational calculus. Again, we're recognizing all these words, right? This is a row inside of a table, and we're going to do calculus with it. This is, some sort of, I have some passing familiarity with algebra, and I know that this has to do with what's relations? Tables. Algebra with tables. And then we have domain relational calculus. You remember what domain is. The domain is all the possible values for a given data type. And tables are built out of data types, a sequence of data types in columns. And so again, another sort of calculus-based, table-based language that focuses on data types. Again, that's a non-procedural language. If you, as a computer science major, who you know that you're about to be assigned a slot on the team that's designing the new database, you're not necessarily going to be the main programmer, because thank God you don't know what any of these 3 pure languages are, and probably the main designer is going to need to know at least one of them. But if you had to choose from this list what language you would be most comfortable learning, Veda, which one would you choose? That just sounds easiest, right? I don't actually know if it will be easiest, but from my experience, algebra was easier than calculus.
I'd say domain relational calculus. I feel like that's going to be way more fun.
Well, fun does not mean easy, dude. I am a lazy computer programmer. I would like to learn the minimum new information possible in order to do my next job. Yeah, I think that most of us would probably choose something that seems familiar. And so my whole point in presenting these three values to you is to make you guys hate these two options and be grateful as we're slogging through the next few slides, chapters, that we're doing it in this and not these.
You're too late for me. Calculus is already familiar.
You're going to drop the class now. Oh, we're not doing calculus? Screw this. All right. Let me talk about the 5 basic operations that we're going to try to represent in some sort of mathematical, algebraic, hybrid form. What do databases do? Databases select a group of data to copy out of the database and transmit to your computer and show on your screen. So that's the selection operation. There's also a projection operation. Once you have the data on your screen, sometimes you don't need to see every column of your data. Maybe you're only interested in 2 of the columns. You remember in class last time, I think, when I showed you the result of a join operation where it was taking all of the columns from the actors table, all of the columns from the glue table, where those values didn't even make sense to most of us, and all of the values from the movie table, right? And just concatenated everything into one great big super long row. But remember what those check marks did in the design view of the queries? Is it showed, it told Microsoft Access, these are the column values that I actually care about. I just want to see movie name and actor name. I don't care what their IDs are, those numbers make no sense to me. I just want to see movie name, actor name. That's how I want to see that list. That's what projection does. You're given a list of probably all of the possible attributes that are being glued together, but you are filtering out only the ones, you're filtering out the ones you don't care about. You're only displaying the columns that you do care about. That's the essence of projection. And I'm going to be talking about these individually again. I'm just giving you a big overview now. Oh, I think normally when I present these, I show you the mathematical symbols that I'm going to use with each of them. So selection, that starts with an S. What does a mathematician do when he wants to show you an S? He's going to go straight to the Greek alphabet. How do we represent S's in Greek? Why Greek? Those were the smart people. Didn't they come up with algebra or something? What is S in Greek? Anybody? Sigma! You remember mathematicians telling you sigma and you're wondering why are we not using English words anymore? Sigma is the name for the letter S in Greek. It looks like this. I mean, there's also capital sigma. I bet you guys have seen capital sigma. It's that guy, right? I keep on drawing that guy for you in class. But we're not going to use capital sigma for selection. We're going to, every time we do selection mathematically, represent selection mathematically, we're going to be using lowercase s, lowercase sigma. Okay, projection. That's going to be capital P. There's no rhyme or reason to capital or, I think they just chose what looked prettiest to them. And so capital P, what is P in Greek? The letter pi. Capital pi, lowercase pi. We're going to use capital pi for this one. That's projection. I'll just select, project. Hopefully that's visible in the video. Cartesian product. What is a product in math class? It's like multiplication, right? Multiplication is happening when we're talking about products. And Descartes was the guy that the Cartesian space was named after, the XY things that we graph points on. Cartesian product, we're going to use the product symbol, multiplication sign for that. Or maybe it's capital X or something. Does that come from Greek? I don't know. We're just gonna call that capital X. Union. You guys remember the union sign. You've probably seen that when you want to take the contents of two sets and put them all into the same set. Set A, union set B. You've probably done that in a high school math class, and so I guess that's capital U is what that looks like to me. And that probably also has a different name in Greek, but we say U because we're Americans. And set difference. What's differencing in a mathematical language? When we're taking the difference between two values, that's like subtraction, isn't it? We're going to use the subtraction sign. Set difference. Of all of these basic operations, these three are probably the ones that we're going to see the most. This is the one that we affect 90% of the time, but then also whatever we select, we're selecting everything, and so we usually do a projection of whatever our selection was. This set difference is actually the rarest one that we see, but the reason that we talk about these as the 5 basic fundamental operations of relational algebra is because everything that we do in a query language, everything that we're going to do, like, you know that one of the things we're going to want to do is join tables together. So that is another operation, but I'm not showing you that symbol yet because it's not one of the basic operations, it's not fundamental, but we can put those basic operations together in such a way that they will do a join. And so that's the difference between the fundamental ones and the non-fundamental ones. Oh, yeah, okay, yes. And this one is going to be the most important of these three. This is the one that we do all the time when we do a non-fundamental one. Sometimes we care about what's common between two tables, but that's relatively less common. And then division is the one that all the students hate. Because division has nothing to do with mathematical division. It doesn't even make sense that they named it like that. But it's also something that you don't feel like, it's something that when I teach it to you, you're going to wonder to yourself, when am I ever going to need to do that? And of course, you are going to need to do that in a database system like 2% of the time. You're going to need to implement it. But it's sort of hard to come up with an example where, oh, I really need to do the division operation on this thing here. So we'll hit all of these individually over the course of the next couple of weeks. This is just an overview, and we're just going to be using a bunch of mathematical symbols for most of that time. It's going to be great for everybody who missed class today. All right, thank you very much for your attention. I will next see you back here on Monday. Have yourselves a good weekend.
Okay.